Hello everyone, I'm honored to have this opportunity to present our MEng project to you. Our project is based on the noise assessment and the localization in London Underground. Let's start with the background. First, London Underground has more than 150 years history since its first operation. Therefore, there are several lines which have operated for quite a long time, and the track as well as the tubes are probably in the aging process. We could usually hear a quite loud noise in some of the lines such as Northern Line and the Victoria Line. Also, public transport occupies 35.5% of total trips in London, and London Underground carries 1.4 billion passengers annually. So for a single person, normally you have 253 working days every year, and then twice a day for commuting, and therefore 506 commuting times at least every year. Also, there are construction workers and engineers inside the underground. This drew our attention regarding to if the noise in the London Underground will cause damage to humans' hearing. If the noise does damage people's hearing, we call this the noise-induced hearing loss, which damages the hair cells in the cochlea of human's ear. So the reason we are doing this project is to find out the noise level with respect to the distance inside the London Underground. There are researchers measuring the noise level for each station, but our project is unprecedented by author's knowledge because we are using accelerometer to tackle the problem that GPS is not available in the underground. So our aim is to build a sound level meter which is detectable between humans' hearing range 20 to 20 kHz. Then in order to make it compatible to the noise at work regulation, the device should be well calibrated and able to convert the signal into the equivalent continuous A-weighted sound pressure level and compare with the specific value mentioned in the regulation. In terms of the localization and the positioning, we utilized a 3-axis accelerometer, and through mathematical methods such as double integration of the acceleration from the accelerometer, we obtained the relative distance of the tube. Other than that, for data storing, we want high resolution of logging data to achieve high quality of the signals for the entire duration of a single journey. It should be also protected inside the box and safely powered through the whole journey. Then we conduct measurement in Victoria Line and the Northern Line and process and analyze the data. Through Fourier transform and other techniques, we have our spectral analysis and color map for the noise level. I'm mainly responsible for the audio part of the project, including the microphone circuit, the calibration, and processing the signal to the equivalent continuous A-weighted sound pressure level. The omnidirectional microphone we used has a detectable frequency range between 20 Hz and 20 kHz, as well as a general sensitivity of 45 plus and minus 2 dB from 20 to 2 kHz. In order to allow the microphone to operate at a standard operating voltage of 4.5 volt, the microphone is in series with a 2.2 kilo ohm resistor and powered by a 5 volt DC voltage. The signal from the microphone needs to be amplified before transmitting into the microcontroller, as the microcontroller used in the project has an input range between 0 and 3.3 volts. So the aim of the amplifier circuit is to amplify the signal without crossing the limit, but also implementing a DC bias level at 3.3 divided by 2, which is 1.65 volt, to keep the entire signal intact. In terms of the portability of the final devices, we chose an amplifier that can be supplied by a single power supply of 5 volt or 2.7 volt without applying a negative voltage at minus Vs. Before setting up the desired gain, raw data without amplification from the microphone has been recorded by taking measurements between Camden Town and Leicester Square Station in Northern Line using an AC voltage meter. The table on the bottom left shows the maximum detection as well as the base noise between each station. This allows the gain to be set in a certain value to prevent the signal exceeding the boundary between 0 and 3.3 volts. In this case, the gain is set as 12.3. Next is the calibration of the device. The picture shows the calibration process of the device. The process is done in the open field. The sponges or the absorber also make sure only very little sound is reflected to affect the result. The device is put at the same level of a reference SPL meter, which has a 30 dB to 130 dB measuring level range from 31.5 Hz to 8000 Hz. We used an app from the mobile phone that is able to play tunes at different frequency and different amplitude. The microphone was connected to an Arduino for taking voltage readings for a certain level of sound, then the reading from the SPL meter in dBA is called the sound pressure level or the acoustic pressure level. This is defined as the pressure difference caused by the vibration of sound wave passing through the media. Then we convert the reading into pressure and we combine with the reading from the Arduino, we get a value in millivolt per Pascal. The datasheet of the microphone provides a sensitivity in decibel or millivolt per Pascal, and as a result, the calibration factor can be calculated at each frequency value. For the accelerometer, amplification is required to satisfy the maximum resolution of the ADC, but also between 0 and 3.3 volt at the same time. The analog signal from the audio and the accelerometer first flow into a 12 bits analog to digital converter. We are using the same sampling frequency at 50 kHz for both the audio and the accelerometer. Then the digital signal goes into a first in, first out buffer and stored in the SD card through the SD bus mode. This is the final device for our design. The left picture shows all the components of the device. The right picture shows the device covered by the protection box built by our team member via 3D printing. Here are some results for the Victoria line, where the blue curve on the left indicates the total noise level against distance, or the station, and this is for the northbound. And this is for the southbound. I would like to highlight some results between both bounds. The dominant frequency range of noise in Victoria line lies between 0 Hz and 100 Hz, followed by 100 Hz to 300 Hz, and then 300 Hz to 1 kHz. The noise over 1 kHz is relatively small among all stations at around 80 dBA, while noise between 1 kHz and 3 kHz sometimes could reach around 90 dBA, for instance from Highbury Station to King's Cross Station southbound. Generally, northbound is noisier than southbound, but the most unpleasant noise segment appeared in southbound at around 112 dBA from Vauxhall Station to Stockwell Station, and 105 dBA in northbound. Another phenomenon that should be worth attention is the noise between 300 Hz and 1 kHz in northbound increased significantly between Brixton and Stockwell. This also happened to the noise between 100 Hz and 1000 Hz after King's Cross Station in comparison to the previous stations. By looking at the peak values in southbound, such as those between Seven Sisters Station and Finsbury Station, Highbury Station and King's Cross Station, it can be seen that 300 Hz to 1000 Hz noise is the main component. Here are some results for the northern line, where the blue curve on the left indicates the total noise level against distance. This is for the northbound. This is for the southbound. In terms of northern line, overall, the main dominant noise is still from 0 to 100 Hz. However, noise between 3 kHz and 10 kHz is incredibly large at the beginning of northbound, from Morden Station to South Wimbledon, which is higher than noise from any other frequency band at an average of 100 dBA. The worst noise appeared in northbound between Kentish Town Station and Tufnell Park Station, reaching roughly at 112 dBA. Again, it is also noticeable that among the entire line, when the noise reached some peak values, the main component is still from 300 Hz to 1 kHz spectrum. The general noise level starts to drop before Highgate Station in northbound or after in southbound to approximately 95 dBA. This is mainly because the tube is no longer in the underground, instead in the open field. From that, noise from different frequency bands drop at different extent. Noise between 100 Hz and 300 Hz decrease very slightly, while noise between 300 Hz and 1 kHz decrease more significantly to no more than 80 dBA. There are also cases of noise between 1 kHz and 3 kHz in southbound, increasing largely to more than 95 dBA, for instance between Kentish Town Station and Camden Station, between South Wimbledon Station and Morden Station. Combining with the colored map, I apologize that I cannot make it clear enough. Both Victoria Line and Northern Line have a worse performance in northbound, which are assessed by the number of segments over a noise level of 100 dBA. In comparison, though Northern Line has a great performance among the open field journey, it still has more number of segments of noise level over 100 dBA than Victoria Line, especially in northbound service. What's more, it can be also seen that for both directions, high-level noise in Northern Line is mainly in the south part, which is between Morden Station and Tooting Bec Station, as well as the city central, between Kentish Town Station and Charing Cross Station of the journey, while high-level noise in Victoria Line appeared through the entire line. Our team member also developed an user interface using MATLAB, which is able to plot noise level against stations for different bound and different lines. Users can zoom in and zoom out the plot in order to have a clearer look of the noise level between two specific stations. What's more, plots for different frequency range are also available to users. Then we also have something to do in the future. First is the better outside shield design, since our current box through 3D printing produce a two-piece box instead of just one piece. There is no heat dissipation in the design, so in the future, enhancing the stability and the function of the box should be done. Then is the calibration. The calibration has to be done more professionally in the future. To make it more accurate, the calibrated microphone or the SPL meter should have a detectable range of sound between 20 Hz and 20 kHz. It should be also done in a place where no reflection of sound would take place. Also, we only testify the precision of the localization with the datasheet given by the TFL. However, to improve accuracy and precision, it is also necessary to try other different techniques to know if there are better ideas of localization. Finally, we also want to finish our color map on the other 13 remaining lines. Here are some references that are included in the PowerPoint. Thank you very much for your listening.